it's the most significant bit. You know, it makes sense because if there's anything in the most significant bit, if there's any 1 in there, it's obviously greater than the next than a number that doesn't have anything in there. So what you have to do is set up your numbers. Let's stick with a 4-bit example. A2, A1, A0, B3, B2, B1, B0. What you got to do is just compare bit by bit going this way from MSB to LSB. So first off, what you do is if A3 is a 1 and B3 is a 0, stop right there. We already know A, oops, A is greater than B. Now, if A3, let's just say, now let's say B3 happens to be a 1, well, in this case, they're equal, so we don't know. And you got to look at the next position. So then you go to A2, B2, let's just say that's a 0, and this is a 1. So now we've walked down from the MSB to the next digit. Now, knowing what we know from binary, up here, we know that B is greater than A, or, because there's only really one output, well, there's 3 outputs, but they're pretty formalized as A is less than B, okay? And so you just keep on going. All you do is just keep on walking down to the least significant bit. Key is the higher order inequality takes precedence. Using this example right here that we had upstairs, 1 0 0 0 1 1 1, you're walking this way. So, you know, it's got to compare this digit with that digit, and A greater than B. If we walked this way, we started with LSB, well, 1 is greater than 0, and yeah, it just wouldn't work. So, 4-bit comparators. So this is what a functional block diagram looks like of a 4-bit comparator with something conspicuous missing, which we'll talk about in a couple of seconds here. So a 4-bit comparator obviously has an inputs for your A, 4-bit number A, and your 4-bit number B, and it's got 3 outputs where they're high. If A is greater than B, this one's going to be high. Whoops, I don't know why I drew a 0. And these guys will be low. If they're equal, like that, and if A is less than B, you're going to have an output like that. Okay, so this is the functional map, the 7485. Pin diagram, totally different. There's map for the pin diagram in your book, and that little Bible, the TTL Bible. So what are we missing here? Well, it's this stuff right here. There is also an input. So this is the outside. That's the inside. For these things right here, where A is greater than B, A is equal to B, and A is less than B. Well, what does this do? Well, this is used for cascading a 4-bit comparator with another 4-bit comparator, thereby giving you an 8-bit comparator. And the key to doing that is, well, first off, connecting them correctly. And how you do that is here, let's see, I'm going to go ahead and pause and redraw it. So you put them right next door to each other. And if this is the LSB and that's the MSB, you feed the LSB's outs to the MSB's ins. And basically, like we said before, higher order bits get precedence for equality, or for that matter, inequality. So these are still the outputs right here. But what it is you are feeding now A4, A5, A6, A7, B4, B5, B6, B7. So you are still checking A7, A6, A5, A4 compared to B7 through B4. And if you still get a point where it's equal, then you got to go back to these things, and it's giving you the outputs of whether the lower order bits are greater than, equal to, or less than. So the key thing is here, though, is you got to put this guy, this least significant bit, this guy has to be +5 or high for that matter, because, i.e. 0 equals 0, because it's already starting off at an equal state, high. And these guys have to be to ground, because that least significant bit, the lower order stages, basically it's not unequal. It is equal because 0 equals 0. So least significant bits, hands off its results to the higher order section, just in case all these numbers up here happen to be equal. It can look back and say, okay, is the lower order bits, is that making it higher, lower, or in between? How to cascade it to a 12-bit, you just put another 7485 right there, 16, another one, another one, another one, another one. Okay?